Welcome to the lecture for Wednesday, February 19th. So today we'll be talking about rotational motion. By rotational motion I mean an object that's spinning around in a circle. So for example, look at this little metal sphere that's attached by, actually it's magnetic, that's how it's attached to this CD. As the CD spins, the object moves around in a circle, and you notice that this motion, how fast the object is moving, is determined by how fast the CD is rotating, as well as what is the radius at which the particle or the sphere is sitting at relative to the rotation point. Okay, so for given angular speed, how fast the CD turns, the bigger the radius is, the faster the actual object is moving. Okay, so we'll be talking about that today. So we will consider a particle going around a circle with radius r. Okay, so let's make a plot. Here is a two-dimensional plane with the x and the y axes. And here is my circle. Okay. And the particle, let's say, is right here. It's going around the circle, let's say this way. Going around circle. Let's say that the circle has a radius, well, we already said it has a radius of r. Okay, that's this distance. And let's say this is an angle theta. Okay. Now, I also want to define something over here that's this distance from here to there, this guy. This is what we will be calling, well, it's what's called the arc length. And we'll just call that small s, small s, not capital S. Okay, so capital R is radius, small s is the arc length. So theta, so we let, if it's not clear, let theta be the angle from positive positive x-axis. Measure counterclockwise in the usual convention. So we start here on the positive x-axis and we measure it counterclockwise. This is clockwise and this is counterclockwise. So we're measuring the angle like this. Okay, for this discussion, this is the first time that the unit of radians for the angle will be important. So you have to be a little bit careful here in making sure your calculator is set on radians and converting back to degrees when you need it in degrees. So we're going to measure, it'll be convenient to measure theta in radians. Okay, so remember 2 pi radians is equal to 360 degrees. 2 pi is one full circle around. So therefore pi is 180 radians and pi over 2 is therefore 90 degrees. Okay. Now, the reason this radian unit is helpful is because the arc length here, this s, is very simply related to the radius and the angle in radians. So the arc length, S, you may recall this from, I guess, probably high school geometry, that if I have this angle measured in radians and r is the radius, then the arc length is just r times theta, where theta is in radians. If that's something you have forgotten, you can kind of convince yourself that that makes sense, because if theta, the angle in radians, is 2 pi, or 1 full circle, that's going around the whole circle, that will be just r times 2 pi r, which is the arc length going around a full circle, which is the circumference. So that's where the formula 2 pi r, you can get that from this argument. Okay? But it's true in general, the arc length is going to be proportional to r and proportional to theta, and just multiply them together. Okay, now the next thing we will do is we're going to consider a small change in the theta value. So we'll call this an angular displacement, sort of an analogy with what we did with one-dimensional motion with x. Okay, so we consider an angular displacement delta theta during time interval delta t. Okay, so what we're doing is we have some initial theta. So theta, remember, is measured relative to the positive x-axis. We're just going to consider a small change in theta in a given time delta t. So there's a delta theta change in a time delta t, and so if we have just a very small interval, we can think about an average angular velocity. Okay, so the definition is the average angular velocity, and this will be written as okay, so for all the angular stuff, we're going to be writing down formulas that involve Greek letters, but it's actually not so hard to figure out what's going on if you just make some simple analogies, and this is something I will keep stressing throughout today's lecture. So the symbol for the angular velocity is this omega. That's a small omega, Greek letter omega. It's not a W, but if you write a W, nobody's going to be horribly upset. That's an omega. Okay? So omega average is delta theta over delta t. Oops, sorry. Is delta theta over delta t. Okay? So this is supposed to remind you of V average, the average velocity, but now it's the average angular velocity. So that's supposed to say delta theta over delta t. And this has units of radians per second. Okay. Now, one thing that's kind of funny with angles is that this thing, radians, or this thing, degrees, it's not really a unit in the same sense of meters or seconds. It's actually something that really doesn't have a unit. 2 pi is the same thing as going around one time. It's like rotating one time. That really doesn't have a true unit. So sometimes you'll find it convenient to just drop the radians when you want to drop the radians. So you'll see funny equations where you have radians all over the place, and then in the final answer you just drop the radians, and that's just sort of implicitly done sometimes, or just drop the radians at 1/seconds. Okay. Now, we can also talk about the instantaneous angular velocity. And this is the analog of the instantaneous velocity that we did before. And so now we just write omega, so this omega without the average, and that's equal to the limit as delta t goes to 0 of delta theta over delta t, and that gives us the time derivative of theta. Okay? So this also has units of radians per second if we're being careful, or if we're playing this game where we just don't even consider the radians as a unit, just 1 over seconds. Alright, so if you have any questions about angular velocities, average and instantaneous angular velocities, please give me an email. I should be able to receive and reply to emails during my trip to Vancouver. The next thing we'll talk about is acceleration, angular acceleration. So now what we'll do, just like we did for regular acceleration, we'll talk about a change in the velocity, or the change in the angular velocity. So now we're going to consider that this instantaneous velocity is changing with time. So we're going to consider a small change in this velocity. So consider change in the angular velocity. By the way, when we don't say average or instantaneous, and we just say angular velocity, we have in mind instantaneous velocity. That will be the default. Just like when we just say velocity, we mean instantaneous velocity. When we just say angular velocity, we mean instantaneous angular velocity. So consider a change in angular velocity, or instantaneous angular velocity, delta omega, during a time interval, during time interval, delta t. Okay? So we can then define the average angular acceleration. Alright, this notation is once again going to be a Greek letter, and we're going to take the closest thing to the letter A, which we've used for acceleration. So this notation is kind of transparent. We write alpha average, and that will be delta omega divided by delta t. Okay. And this will have units of, well, let's see, omega has units of radians per second, so then delta omega over delta t will have units of radians per second squared. Or if we're playing this slightly sloppy game of not writing all our radians out, 1 over seconds. Okay? Alright. Now, we can also talk about the instantaneous acceleration. Instantaneous angular acceleration. I have to stress angular, instantaneous angular acceleration. And this will be the limit as delta t goes to 0 of delta omega over delta t. Okay, and that gives us the time derivative of the angular velocity. So the angular acceleration, the instantaneous angular acceleration, is the time derivative of the angular velocity. So once again, if we just say angular acceleration, we mean by default the instantaneous angular acceleration. So all this stuff should remind you of the things we did pretty much in the first couple of lectures of the course for motion along the x-axis. All right, now we're going to actually end up doing a lot of the same things that we did back in the first couple of lectures. So I will try to frame this in terms of analogies. So I'm going to make what I'll call the linear dash angular correspondence. So the purpose of this is that you don't have to memorize anything anything new again. Just making correspondences will allow you to dig up the information you already learned for the motion in a straight line. So let's consider the linear case, the stuff you already know, and the angular case, the new stuff. Okay, so first of all, let's consider velocity. Okay, for velocity, we call this v, and the units are meters per second. Okay. And for angular velocity, over here we have angular case, we call it angular velocity, and the symbol is omega, small omega, and the units are radians per second, or I'll just write the lazy way, 1/seconds. Okay, next comes acceleration. And for the linear case, motion in a straight line, we have the acceleration A, and that has units of meters per second squared. So remember, everything we're doing here is instantaneous velocity, instantaneous angular velocity, instantaneous acceleration, and now for the angular case we'll have instantaneous angular acceleration. So it'll be radians per second squared, or just dropping the radians, 1/seconds squared. Okay, now if we have constant angular acceleration, when we have constant angular, sorry, my writing has suffered on that. Let's try that again so you can copy that a little better. Angular acceleration. We can use the corresponding equations. Which I'll write down in a second, but let me try to explain what exactly is constant angular acceleration. Okay? So it's talking about the rotational speed of the, let's go this way, of the CD. Okay? So, alright, so I have to stop to reload my finger to make it turn, but forget about that. Just pretend it's going smoothly with a constant angular velocity. Okay, this is approximately a constant angular velocity. But suppose now it starts to speed up. Okay, that would be actually angular acceleration. So what we're considering is constant angular acceleration, where the acceleration is increasing with a constant rate. Okay, so the angular velocity is getting larger and larger with a constant rate. So it starts off slowly and it gets faster, or let's suppose it's going at some speed and it just slows down. Alright, so this has a clear analog with linear angular constant acceleration problems. And so you had a bunch of these things that you learned from the previous material. So the linear case for constant A here. So remember these formulas, these guys you probably remember. V is equal to V0 plus A times delta t. What's another one? Delta x is equal to V0 delta t plus 1/2 A delta t squared. We also had the V squared formula, V squared minus V0 squared is equal to 2A delta x. And we had another one, in case it's useful, V bar, the average. Okay, V bar or V average is 1/2 V0 plus V. Okay, by the way, the notation I've been using is this. In my notes I had it as V bar. Okay, now on the angular side, angular for constant angular acceleration, alpha. In this case, we just plug in these. Wherever you see a V, you write in an omega. Wherever you see an A, you write in an alpha. You don't even have to think about anything else, and you get the new formula. Omega for V, omega naught for V naught, alpha for A, and delta t remains the same. Okay, so that tells you how to get the final angular velocity from the initial angular velocity and the constant value for the angular acceleration. We can also get delta theta. Alright, maybe perhaps I should have included that here as well, so we could have snuck in position as well. We could sneak in here position, or displacement, x. Okay, and that's measured in meters. And then for the angular case, you get a theta. Okay, and that really has units of radians, but since we're dropping radians, you can think of it as units of pretty much 1. Okay, so delta theta is equal to the V naught becomes omega naught. The delta t just remains delta t, and then we get a 1/2 alpha delta t squared. And then the next equation we have omega squared instead of v squared minus omega naught squared, and then times 2 times, instead of a alpha, instead of delta x, we get delta theta. Okay. And now we have omega instead of v, so omega average, or the omega bar, whichever notation you want, is equal to 1/2 omega naught plus omega. Okay, so you just make these correspondences and you solve the problem pretty much the same way. To make this more concrete though, let's do an example. Alright, if you have any questions about this at all, please give me an email and I'll try to reply as quickly as possible. So let's do an example. And the example will be a watch that is slowing down with a constant angular acceleration. So the example is the seconds hand on a watch starts with the proper speed. Proper speed meaning the proper speed that a second hand should have, the seconds hand on a watch should have. So that it goes around, sorry, I'm going the wrong way. So it goes around like this clockwise one time in a minute. All right. So with the proper speed, but then slows to a stop uniformly. And so that's a little vague. What I mean is with constant angular acceleration. But it does so over a period of 1 day. So this watch pretty much is slowing down, and the second hand is, after exactly 1 day, it's actually not moving, which is kind of bad. Now the question is, what is the angular acceleration alpha? Okay, this constant angular acceleration, and how many radians does the seconds hand rotate during that time of 1 day? Okay. Alright, that sounds kind of complicated. It may be kind of confusing because I gave you absolutely zero numbers except for saying 1 day, and so maybe it's hard to see how to start this problem, but let me try to show you it's not that hard. So let's consider what's going on initially. So this is a second hand on a clock, so it starts off at 12 o'clock, pointing towards 12, and it rotates like this. Okay, goes to 6, and then goes back up to 12. So it does one rotation in the time of 1 minute. That's what a second hand is supposed to do. So you have one rotation per 60 seconds, 1 minute. All right. So from this we can calculate the initial angular velocity. So omega naught is the initial angular velocity. So that's one revolution of the second hand, and it's during a time of 60 seconds. And one revolution is the same as one cycle around, or that's one circle, that's 2 pi radians. Okay, so that will give us, plug in the 2 pi, 6.28 is 2 pi divided by 60 gives us 0.105 radians per second. Okay. Right, so the next thing to note is what the final situation is. The final situation is that the second hand is not moving. Okay? Now, from this, we know we have omega naught, we have omega. We can go back to our list of equations and try to figure out alpha. So we have these equations here. So it looks like this guy will help us. We know omega naught, we know we know delta t, and we can solve for alpha. Alright, so let's do that. So we can get, so let me write it down. Omega is equal to omega naught plus alpha times delta t. So alpha is equal to omega minus omega naught. Bring these guys to the same side. And then divide by this factor delta t. Okay, so now omega was 0. Omega naught is 0.105, so we get 0.105 with a minus sign. And then we have the time, which is 1 day. So a day is 24 hours. I'm just doing substitution method. An hour is 3,600 seconds. And so we have 1 times 24 times 3,600. That's going to be 86,400 seconds. And so we'll find that alpha is minus 1.22 times 10 to the minus 6 radians per second squared. Okay. All right. So if you have questions about this, please give me an email. Now we'll move on to the second part. After we get alpha, the question is how many radians does the second hand rotate? Alright, so we need to figure out delta theta. So we have delta theta, these two formulas. We can use pretty much either one. We have delta t now, so we can use this equation, so might as well just use that. That's what I did in my notes. Okay, so what we'll do is we will say that delta theta is equal to omega naught delta t plus 1/2 alpha delta t squared. And then plug in that omega naught is 0.105 radians per second. Delta t is 86,400 seconds. And then alpha, we've calculated as negative 1.22 times 10 to the negative 6th radians per second squared. And delta t is 86,400 seconds, and we square that. Alright, we calculate this through. This guy becomes 9,700 radians. And then this guy over here comes out to 4,504 radians when I plug that into the calculator. And I get 4,520 radians. So that sounds like quite a lot of radians. That's actually because the clock is actually going. Sorry, I keep going the wrong way. The hand is rotating, and it's gradually slowing down. But it does it over the course of one full day, so that's quite a large number of rotations. Okay, so if you have questions on this example, please let me know. Give me an email. We will go on now. We're going to now relate some quantities to some things we already know about circular motion. So let me motivate this. If we know the angular speed of the rotation, so how fast the angle is moving, we can actually determine what is the speed of this little object at a given radius r. Okay, so if the object is very close in, then it's not going very fast at all. But if it's way out on the edge, a large radius, for given rotational speed, it goes much faster. Okay, so let's work this out. Let's draw this picture again. Let's draw not the whole circle. Let's just draw a little section of the circle, and we have a little delta theta here, and we're going to have some arc length. That's this guy here. Okay, let's call this S. That's the arc length. actually, to be consistent, I really should call it delta S because it's a small arc length. That might be better notation. Okay, so if I have some time interval delta t and the object goes from here to over to there, then the speed, which is the magnitude of the velocity, obviously, speed is v is equal to delta s over the time. Okay, that's how far it goes, and that's the time delta t. So you divide the two and you get the speed. Okay, now we also know that this arc length delta s is equal to this radius of the circle, okay, times this angle, right? This thing is, by the way, this is what's called the sector of the circle, and this is the angle for that sector, and this is the arc length for that sector. So delta S, we just said, is equal to the angle measured in radians times r. So I'll write that as r times delta theta, where theta is in radians. Okay, so we have an expression for delta S, and we're going to plug that in here. And so we'll get that V is equal to, instead of delta S, I'll write R delta t, the theta, divided by delta t. And then I'll rearrange things, so I'll have delta theta over delta t times R. Okay, but you'll notice that this thing is the same thing as, in the limit as delta t goes to 0. This guy is my angular velocity. Okay, so this guy becomes omega. So we have this relation that how fast this object is going is r times the angular velocity. Okay. All right, questions about this or anything relating to this, please give me an email. The next thing we'll talk about, by the way, I should probably mention, so we've been calling this the angular velocity. If we just want to talk about the magnitude of omega, because omega could be positive in this direction, or it could be going the other way, it could be negative. If we just talk about the magnitude of it, we'll call it the angular speed. Okay, so it's kind of like one-dimensional motion where you just take the minus sign off, where you just take the absolute value to get the speed. Alright, now let's consider the case where we have the angular velocity is changing with time. Okay, if angular velocity is changing with time, then we can think about, this is this case where it's actually speeding up, it's getting faster. Okay, it was going slowly, then it's getting faster. Then there will be some acceleration that will be tangent to the circle. There will be some acceleration going because the object is actually getting faster. The speed is getting faster. Okay, so we can talk about a tangential acceleration. If angular velocity is changing with time, then we have a tangential acceleration. We've already talked about tangential acceleration, but let me remind you. So we have the circle, we have an object. Okay, here's the radius. Here's the radius of the object. If it's actually, the speed is actually getting, let's suppose it's getting faster. It's going around, it starts off slowly, then it goes around more quickly. Then there will be some tangent to the circle. There'll be some tangential acceleration like this, in addition to the radial or the centripetal acceleration, which we'll mention in a second. So the tangential acceleration, tangent to the circle, well, this is the tangential acceleration. Is dv, the derivative of the speed. So this guy is just a plain old speed. Okay? Alright, right, so this is something we learned already, the tangential acceleration, but now what we can do is we can take this formula we just derived, that v is equal to r times the angular velocity. Okay. Then we will have, so we can say v is equal to r times omega, and then we'll see that at, the angular tangential acceleration, sorry, I said the wrong thing, the tangential acceleration is the time derivative of r times omega by dt. Okay, now it's just going around a circle, and the radius is not changing, so this is just a constant, so that comes out in front. But we do get a derivative of the angular velocity. Okay, the derivative of the angular velocity is the angular acceleration. So we have derived a formula that the tangential acceleration is just r times the angular acceleration. Okay? It makes some sense from the point of view of units. Acceleration is meters per second squared, r has units of meters, and alpha, dropping the radian stuff, is 1 over a second squared. But this is actually why we like to drop the radians, so that we don't have radians, extra radians floating around in equations like this. Okay, but to complete the question about acceleration, though, this is just the tangential component of the acceleration. There's also going to be some radial acceleration. Okay, this we already know as the centripetal acceleration. So there's also the radial or centripetal acceleration. So remember, in order to go around the circle, we need some acceleration pointing inwards towards the center of the circle. And the formula is the same as we had before. The radial acceleration is AR, is v squared over r. So that's the radial or centripetal acceleration. Radial or centripetal acceleration. Okay, but now we once again have this formula for v. This guy here. So let's plug that in here for v. Okay, so we'll have r times omega squared divided by r. So we'll have r squared omega squared over r. Okay, so that gives me r omega squared. R omega squared. So that's another formula for the centripetal acceleration. If you think about something, you know, going around, so this object here, in order to go around a circle, let's just make a uniform circular motion. There's going to be a centripetal acceleration pointing inwards towards the center of the circle, and it will be equal to, well, you already know the formula v squared over r, but you can also write it as r times the angular speed, angular velocity omega squared. Okay? So the formula is AR is r omega squared. And again, you could have kind of guessed this formula just by remembering the v squared formula. So you need probably 2 factors of omega. And to get the units right, the radial or the centripetal acceleration has units of meters per second squared. And so if we multiply the radius, that gives us a unit of meters. And so, and the angular velocity has units of 1 over seconds. So both sides will end up with meters per second squared. And once again, to review, and the radial acceleration points radially inward. That's always the case. That's needed to go around the circle. All right. Very good. So that's actually the end of the new material. So if you have questions about this, please give me email. In the time remaining, though, let us do a review problem. This is the reason for doing these review problems is there's kind of a large time period during which we cover test 2 material, and I want to make sure that that everything is fresh in your mind by the time we get to test 2. So let's do a review problem. We'll do one dealing with non-conservative forces and energy. So let's say a box with mass 10.0 kilograms starts at rest at the top of a slide 5 meters tall. Okay, and so that's actually how high it is. By the time it reaches the bottom, the box is actually going to slide down the slide. Why else would there be a slide? By the time it reaches the bottom, it is moving with speed 1.50 meters per second. And the questions will be: find the work done by gravity and find the work done by friction. Okay, now you can do this problem a couple of ways. In the notes I do it using the work-energy principle. That's that funny name thing where you write delta K is equal to the work done by the net force. That is actually perfectly fine. You can also do this problem by using the formula that the work done by a non-conservative force is equal to the change in the mechanical energy. Okay, that's also perfectly fine. Now, sometimes when I teach this class, I get the question of which one do I use? How do I decide which one to use? If you only had if you wanted to just deal with one formula, my suggestion is to use the work done by a non-conservative force is equal to the change in the mechanical energy. Just use that formula because that's a little bit, I'd say, a little bit easier to use. You end up doing exactly the same equations with almost exactly the same amount of effort. But I think maybe it's conceptually a bit easier. In my notes I do the work-energy principle, but I'm going to do both. I'll show you both. Okay, let's start off using the formula: the work done by a non-conservative force is equal to the change in the mechanical energy. Okay, let's do that first. Okay, now the mechanical energy is equal to K, the kinetic energy, plus the potential energy. All right. So I can write this as delta K plus delta U. So the potential energy I have in mind is the potential energy associated with gravity, right? So in order to solve the first part, the work done by gravity, we also need another formula that the change in the potential energy is actually the negative of the work done by gravity, right? So remember this whole concept that as I lift an object, this eraser, I'm storing energy into the potential energy bank, all right? But the gravity tries to go push down on the eraser, but it's losing. So it's doing negative work. Remember, whenever you'd have a little tug of war or a pushing match and you lose, you're losing, you do negative work. So gravity wants to go this way, but the actual displacement is the other way. So when you do the dot product of the displacement and the force, you get negative number, all right? So I'm storing potential energy, so the delta U is positive if I go this way, and the work done will actually be, so it will be equal to negative the work done by gravity. Okay? Alright, so in order to get the work done by gravity, we can simply calculate what is delta U, and that's a formula that's pretty straightforward, and that's why I think maybe this way of doing it is maybe a tad easier. So let me leave this here. So what we'll do is we'll say, okay, delta U is equal to m times g times the change in the vertical height. Okay? Alright. So now the change in the vertical height, well, we're told that it starts off at 5 meters high and it goes down to the bottom. So that will tell us that the change in the vertical height will be -5 meters. Okay, so we can plug in the mass is 10 kilograms and the 9.8 for G, 9.8 meters per second squared, times 5.0 with a negative sign for delta Y, and that gives us -490 joules. Okay. Alright, but that's delta U. So in order to get the work done by gravity, that will be negative of delta U, so that's positive 940 joules. So let's see if that made any sense. So it starts off up high and then drops down 5 meters. So gravity's pointing down, it actually slides down, okay? So the work done should be, because it actually just goes down and the gravity is pushing it down, it should be a positive work done by gravity. So that's to make sure we got the sign right. So it's positive, not 490. Okay, now what about the work done by friction? So friction is this non-conservative guy, non-conservative force. So we need to calculate, we know delta U, we just calculated. How about delta K? So delta K, we can just simply get that by the final kinetic energy minus the initial kinetic energy. Okay, so the final kinetic energy, that's just, remember K is equal to 1/2 mv squared. So for the final we have 10 kilograms and we have a speed of 1.5 meters per second, quantity squared. And for the initial case, it's starting from rest, so V0 kinetic energy will be 0. So delta K will end up being 11.3. Sorry, not 11.3. Yeah, it actually is 11.3 joules. Okay. Now, the next thing we need is to get the work done by the non-conservative force. So that's the delta E mechanical. Alright, and so that's delta K plus delta U. So we plug in 11.3 joules, and then the delta U was minus 490 joules, and so that comes to negative 479 joules. So that's the work done by the non-conservative force, the force of friction coming from the friction between the slide and the block going down the slide. Okay. So I promised that I would also do this problem using the work energy principle just to show you it can be done that way. Okay, so the way you do that problem by work energy principles, the work energy principle says the change in the kinetic energy is just the work done by all the forces together, W net. Okay, so we don't have to repeat this exercise of calculating the change in the kinetic energy. We got it's 11.3 joules. Okay, so that's just the same as before. Delta K is 11.3 joules. All right, and so that means that the work done by the net force is equal to 11.3 joules. Now, when you use this work energy principle, you have to remember this is the work done by all the forces together, so you're going to now have to split apart the work done by each individual component. Okay, the work energy principle only gives you the total work done by all the forces together. So now let's do the work done by gravity. So we're going to have to do a separate calculation for this. Okay, so we have, let's draw a picture. And by the way, it's this step which makes the work energy principle calculation maybe just a tad more complicated because you have to do this little analysis. Okay, so we have the force of gravity going like this, Fg, and we have this distance, the displacement, okay, how far it goes. Actually, it's going this way, so like that. And let's call this height h. Perhaps. Okay. Now, well, we don't need so many names for that. But let's see. So the point is we need to calculate the work done by gravity. So the work done by gravity is going to be the force of gravity dotted with the displacement, this vector going from here to there. So that will be equal to the force of gravity, which is m times g, okay, that's this guy, times the distance d, times the angle between them. So that's this angle theta. Alright, now you might be worried because they didn't say what theta was, okay? In fact, they didn't even tell you what d was, so you're kind of in trouble both ways. However, they did tell you how high this slide is. So this h, that's actually what they told you. H is going to be the height, but that's actually related to, so this is the right triangle, is related to the hypotenuse d times the cosine of theta. Okay, so that's actually mgh. Maybe that sort of should ring a bell. That's the same sort of formula you get for the potential energy, right? And so we have the force due to gravity will be equal to 10 kilograms times 9.8 meters per second squared times the height 5 meters. Okay, and that gives 490 joules. Right, so that was kind of a lot of work. A faster way to do that, this work calculation, is just simply to say the slide is actually, okay, so what's going on here is we have a motion downwards, but we also have a motion horizontally, so it's kind of going diagonally. If you just simply say that, okay, the force of gravity goes straight down, just completely ignore all the motion in the horizontal direction because it has makes no contribution to the work done, because when you take the dot product, any perpendicular displacement makes no contribution to the work of gravity, which is pointing straight down. So you can just say that I have the force of gravity, which is m times g, or 10 times 9.8, and it moves a vertical distance of 5 meters. I don't care anything about the horizontal distance, and then you can get this answer really quickly. If you know how to do that, then I believe the work energy principle is absolutely just as fast as doing it using the conservation of energy with the non-conservative force, this method. But if you have trouble with this, this is where you could get stuck. Okay, so just think about gravity goes straight down like this. So you just need to consider what is the distance, the vertical distance that's being traveled. Okay. All right, and actually, another way to do it is you can actually use this equation again if you like. You can use this to figure out what is the work done by gravity and just calculate the change in the potential energy. That's another clever way to do it. So I've just given you 3 different ways to do this, actually a whole bunch of different ways you can consider, whether you're using the work energy principle or the conservation of energy with non-conservative force. Okay, but I should shut up and just finish this. We have the work done by gravity is 490 joules. The work done by the net force is 11.3. So there's only one other force, that's the force due to friction. So that must be the work done by all the forces minus the work done by gravity. And so that will be 11.3 joules minus 490 joules. And that gives you negative 479 joules. Okay, so that was a lot of work for a fairly straightforward problem. Please give me an email if you have any questions. But otherwise, I will see you in class on Friday. And I will remind you that I will have office hours at 9:30 a.m. to 11:30 a.m. on Friday. Okay? I'll see you then. Bye.